Good evening, everyone. My name is Jyoti Sharma, and this is week 3, and the live session will be from 7 to 9, and we will start today. The first thing is, am I audible or not? Can you write in the chat box? Thank you, Avola. Okay, so what we will understand today or we will discuss today is about the week 3 and from lecture 11 to 15, in which we will talk about air pollution, then water pollution, and what different mechanism we have or the instrument we have by which we can measure some organic metal, inorganic compound, metal. Likewise, we do have a lot of contamination in the water as well as air. So we have some instrument by which we can measure the concentration of that particular contaminant or pollutant either in water or air. So we will talk about this. So I will start with air pollution. We have a few question on air pollution. Then we will move to water pollution, and we have a lot of numerical today based on water pollution, mostly on hardness, alkalinity, and then absorption ratio. So likewise, we have a lot of numerical question. We will try to solve that, and after that we have some instrument, for example, gas chromatography, then gas chromatography, spectroscopy, then HPLC and spectroscopy. So we will talk about this in the form of MCQs, and I will again encourage you to give me answer in the chat box, and even like you are free to speak and have a good discussion with me. So I'm starting with very basic question. So we have air pollutant, and we have categorized that pollutant into two categories. One is primary pollutant, and the another is secondary pollutant. And you have to tell me the example, which one is referring to the primary pollutant and which one is referring to the secondary air pollutant. So I have four options here. The first is sulfur dioxide and carbon monoxide, nitrogen oxide and ozone, lead and particulate matter, smoke and acid rain. So you have to tell me which one is the primary pollutant and which one is the secondary, and you have to find out a particular suitable pairing. But don't worry, I will tell you the definition of primary and secondary air pollutant if you people do not know. But I want you to guess something about what should be the example of primary pollutant and what should be the example of secondary air pollutant. Can you guess something? Out of these four options, can you guess something? Which one is a primary pollutant? Which one is the secondary pollutant? Any guess? Rough? Okay, I got one answer D, that's smoke and acid rain. Not exact, but nearby. A, not A, not A. Okay, now we have two options only, B and C. So B is the right answer actually. I will tell you how. So just keep in mind right now that primary pollutant example is NOx, that is the nitrogen oxides, and secondary air pollutant is ozone. Okay, let me show you first. Okay, first, very basic slide. I'm starting with a very basic slide. That what do you mean by air pollutant, right? So because we have air act, and under that air act we have the definition of air pollutant, and that is it can be any solid, it can be any liquid or gas that may cause harm or damage the environment, human, plant, animal, or even damage property. So this is the definition of air pollutant according to air act. Can you tell me when this act came into picture in India? Air act. Anyway, so I think you should know in which year the Air Act came into force. And the air pollution we can define as the presence of any dangerous pollutant that will make air unbreathable. And if we are talking about primary pollutant and secondary pollutant, then just keep in mind, whenever we are having any combustion or anything that is happening on the surface that human is doing, and then from source any pollutant is going out in the atmosphere, so that will be known as the primary pollutant. So any pollutant that has been emitted from the source, source may be vehicle, okay, from vehicle how the gases are being released into the atmosphere, so that will come under primary pollutant. Then second, if you are talking about any industries, like if it is a industry of nuclear power plant, let's say, and whatever pollutant is being released into the atmosphere, that will come under the primary pollutant. Then what do you mean by secondary? Then the secondary is whatever pollutant we have in the atmosphere, primary pollutant, that may react with another gas, that may react together, and then whatever will be formed, that will be considered as the secondary pollutant. So if I'm seeing the example of primary pollutant, then this may be the sulfur dioxide, because you know that there is the combustion of diesel, then this will give you the SO2, right? So this will give you SO2. Again, vehicle combustion will diesel combustion or petrol combustion will give you carbon monoxide, NOx, and particulate matter. Any combustion, either like you are using the chula in your kitchen, that can give you the particulate matter. Even the dust we have on the road, that will also give you the particulate matter. So it has been released directly into the atmosphere from the source, so that will come under the primary pollutant. And if I'm talking about the secondary, then this will be as a result of chemical or physical interaction between primary pollutant themselves, or between the primary pollutant and other atmospheric component. And the example is photochemical oxidant. The one is the ozone. Okay, so because we have NOx, and whenever we have volatile organic compound in the presence of sunlight, that will give you the production of the ozone. Okay, so this is the secondary. So NOx, that is the nitrogen dioxide, is already into the atmosphere. Volatile organic compound is already in the atmosphere, that will react in the presence of sunlight, that will give you the ozone. Okay, so that's why ozone is the example of secondary pollutant. So I think it is clear right now. Let me show you again the options. So SO2 and CO both are primary pollutants. So this should not be the answer, right? Lead and particulate matter both are the primary pollutant, and this should not be the answer. Smoke and acid rain both are the example of secondary pollutant, and this should not be the answer. So answer will be nitrogen oxide is the example of primary pollutant. Ozone is the example of secondary air pollutant. That's why B answer will be the right one. Is it clear why I'm sticking with B option, not with A or D? Okay, thank you so much. Okay, coming to the next question. Okay, here again, like this is the picture by which you can understand. So from natural source, from mobile source, from stationary source, these will be the primary pollutant, and then there will be the reaction in the atmosphere among primary pollutant or with another gas, that will give you the secondary. So these are the more example of secondary pollutant you can see here. Either it is nitric acid or sulfuric acid, uh, peroxide, then ozone, pan, and so we do have a lot of example of secondary pollutant as well. Okay, so we have three pollutant in the environment. The one is nitric oxide, the another is nitrogen dioxide, and another is ozone. So you have to tell me the sequence of releasing it from the morning time. So for example, uh, we have the vehicle, and since morning we are running the vehicle. Okay, so which of the gas will produce first, then later on after the time will go on, what kind of gas will release, and subsequently what kind of gas will be released. So there is a sequence of releasing the gas from morning to evening, and you have to tell me the sequence. So I have four options here: ozone, then nitrogen dioxide, and nitrogen oxide, and another is nitrogen dioxide, ozone, nitric oxide, nitrogen dioxide, ozone, and likewise. So can you tell me what should be the sequence of releasing the gas whenever we are running any vehicle from since morning time? What should be the sequence? So the correct sequence of peak occurrence starting from morning hour after traffic emission. Okay, so I'm getting little bit mixed reaction. Someone is saying me D and someone is saying me answer C. Uh, okay, so I should stick with answer C one. I will tell you why. So first, nitric oxide will release. After that, nitrogen dioxide will release, and after that, ozone will release. So this will be the morning time, near to 6 to 8 a.m. Then near to 12 p.m. You can say nitrogen dioxide, and in the afternoon time or in the evening time, ozone will be pick up. So this is the sequence. And let me tell you why this is happening. Okay, just see here. This is the morning time. So let's say this is 8 a.m. So in 8 a.m., we have we have diesel or petrol. In the combustion of diesel or petrol, the first pollutant that will be released is nitric oxide. Okay, then this nitric oxide will react with the oxygen in the atmosphere, and that will give you the nitrogen dioxide. And what will happen? So this is not just the. Let me remove this. Let me give you the more clarification. So first, NO is from the vehicle. That is very clear. Then we have the oxygen, and oxygen in the presence of sunlight, we whenever we will have the sunlight or ultraviolet radiation, then only this ozone molecule will break down into two oxygen atom. Okay, then one oxygen atom will react with this NO, and this will give you NO2. So it means in the morning time, whenever we do not have any sunlight, then the peak will be nitric oxide. Okay, whenever we will have the sunlight and we already have NO in the atmosphere, that NO will react with oxygen, and that will give you the nitrogen dioxide. Then what will happen in the sunlight again? This nitrogen dioxide will convert into this one, nitric oxide and ozone. Sorry, atom of oxygen, and this atom of oxygen again will react with the oxygen, and this will give you the ozone. So this is the sequence. Since morning we have NO, then we have NO2 peak, and then we have the ozone peak, and ozone will give you the smog like condition. So whenever you will see like it will be the after sunlight only, you will have the smog like condition in the places where we do have a huge crowd of the traffic. So the main reason is the ozone production, and this will give you the photochemical smog. So this will be the sequence. I think this is clear. Should we go to the next question? So first we have NO, then NO2, and then ozone. You can tell me whenever you have any query, or if you are thinking that I'm giving you the wrong concept. Anytime you can interrupt me and you can tell me the like whatever you are thinking, right one. Okay, then we do have a concept of criteria pollutant, and you have to tell me which of the following air pollutant is not included in the criteria pollutant. And we have four options here: carbon monoxide, carbon dioxide, lead, and ozone. You are very quick to give me answer, but I'm little afraid that this answer might be wrong. I got answer C. Any another guess that you can have? You can take the lifeline of KBC and you can tell me more options. Okay, Venkateshwara gave me CO2, so that is B. And okay, so I'm gonna stick with option B only, that is the CO2. So see, CO2 is not the pollutant in actual. CO2 is the gas that we already have in the atmosphere, and the increment can give you the global warming or the climate change. But if we are talking about the pollutant or short term smog problem, then CO2 is not the right option here. So let me first tell you what do you mean by criteria pollutant, and then you I think you will understand why CO2 is not the right answer. So I'm going with CO2. So CO2 is not included in the criteria pollutant. And here is the definition of criteria pollutant. So these are the pollutant that has been identified by the environmental agencies. For example, in India, we have CPCB. So in CPCB has defined a set of pollutant that should have a specific standard for allowable level in the atmosphere. So CPCB has given the maximum level of that particular pollutant. Exceeding that particular level can give you the adverse impact on human health or the environment. Okay, so we do not have any such standard or threshold for the CO2, but for another gases pollutant we do have such kind of standard. So the set of pollutant that will come under such standard and that will have adverse impact on human after exceeding that pollutant will come under this criteria pollutant. Can you tell me how many of the pollutant has been considered as the criteria pollutant? How many? Let me show you. Okay, so in India, uh, we do have 12 pollutant for which we have released, or not we, but CPCB has released the standard. And these 12 are particulate matter 10, 2.5, nitrogen dioxide, sulfur dioxide, carbon monoxide, ozone, ammonia, lead, benzene, benzopyrene, arsenic, and nickel. So these are 12 gases for which we do have threshold, and if we are exceeding that threshold, then that will give you the adverse impact either on human or on environment, and this is not for CO2. And let me show you how much. Okay, so can you see, for industrial, residential, rural, or another area, we do have different concentration in the ambient air, and for ecological sensitive area we do have different value of such pollutant. So for example, if it is a sulfur dioxide, then it should be 50 microgram per meter cube, uh, meter cube in the air. So the concentration should be 50 for annual, but for 24 hour it can be up to 80, but not should be exceeded more than this 80. Okay, so likewise we have such kind of concentration for nitrogen dioxide, particulate matter, ozone, and the 12 gases that uh, gases and matters that I already have discussed with you. Now the thing is that whenever we are talking about that AQI, air quality index, so and the calculation of this air quality index, this is mostly based on the criteria pollutant. Okay, and whenever we are exceeding this, then AQI will be more. according to the so I don't think that right now I do not have formula for calculation of AQI, but I think in next week I will show you. But just keep in mind, these are the value that we should not exceed. Okay, and this will come under the criteria pollutant. Okay, now the question is just based on the table that I already have shown to you, and this is annual National Ambient Air Quality Standard for sulfur dioxide in microgram per meter cube in industrial, residential, rural, other area is what? And if you are preparing for the net exam in the environment science, I think that table, this table is very important for you, because mostly one or two question will come out of this table, because we should know what are the threshold values. Okay, so I'm getting Venkateshwara gave me A answer, that is 50, and Priscilla gave me B answer. Okay, so just you have to see this is annual, right? And we do have, like, for annual and for 24-hour we do have different values. So for annual this is 50, and for 24 hours this can be 80 microgram per meter cube of the air. So the answer will be A, right? So I don't think that there should be any problem with this option. Okay. Then, okay, so we do have also some standard methods by which we can measure this criteria pollutant. Okay, so and each criteria pollutant can be measured with very specific method. And for example, if this is the sulfur dioxide, then we do have a very unique method by which we can measure this in the air. Okay, so and you have to tell me the method by which we can measure sulfur dioxide in ambient air. And we have four options here: chemiluminescence, ultraviolet fluorescence, gravimetric method, and non-dispersive infrared spectroscopy. Okay, I'm getting option D with the question mark and D, but I'm afraid that this is not the right answer. Okay, so the answer will be A, that is the ultraviolet fluorescence. And if you are talking about this one, na, D. D is used to measure carbon monoxide. Okay, if we are using NDIR, so this is to measure carbon monoxide. If we have the gravimetric method, this is for the particulate matter. If we have chemiluminescence, this is to measure NO2. And if we have the ultraviolet fluorescence, we have a very particular method, Western Geiger method, I will show you. But along with that, we have one ultraviolet fluorescence method by which we can measure sulfur dioxide in the ambient air. So let me show you that particular slide. Okay, so this is what I got from CPCB website, and they have given that 12 criteria pollutant, and along with that, what kind of method of measurement we should follow. So if it is sulfur dioxide, then the answer will be either West and Geiger method or ultraviolet fluorescence. If it is nitrogen dioxide, then this will be Jacob and Heuster or chemiluminescence. For particulate matter, this will be gravimetric, TEOM, or beta attenuation you can use. And same like for particulate matter 2.5. If it is a ozone, then we can use UV photometric, chemiluminescence, or some chemical method. And because we have 12 criteria pollutant, let me show you another one as well. So if we have carbon monoxide and if we want to measure this, then we have to rely on NDIR. If we have ammonia, then chemiluminescence, or the one method is indophenol blue method. And for the benzene, so whenever we have organic compound, then chromatography is one of the method by which we can measure organic compound, for example benzene or benzopyrene. If it is the arsenic, then we have arsenic or nickel, so these are metals. Then for metals it is AAS, mostly this method that we can have. So you must know, we have criteria pollutant. What are these 12 criteria pollutant that we have, and what are the values for this, and then what different method we have to measure such criteria pollutant. So this is, I think, very important for us to know. Anyway, so we are going to the next question. Okay, I think you can tell me right now. The measurement of ozone concentration in ambient air can be carried out using what? In last table only we discussed what method is used for what criteria pollutant. So if you have good memory, then I think you can tell me, but otherwise it's okay, I will tell you. So we have four options here: UV photometric, beta attenuation. Beta attenuation is for particulate matter. Indophenol blue method is for the ammonia. And this sodium arsenate method is the part of Jacob and Hoyster, that is used for the nitrogen dioxide. So whatever is remaining will give you the answer. So what will be the answer? Can you tell me right now? Beta attenuation is for the particulate matter. Indophenol is for the ammonia. Uh, Sodium arsenite is the part of Jacob and Hoyster method, that is used for the nitrogen dioxide. Yes, so Priscilla gave me right answer. So the remaining one is A. So this is UV photometric method that we use to measure the ozone concentration. So yes, answer A is the right one. Okay, so we have discussed a little bit about the air pollutant, right? Right now we are moving to the water pollutant, and one of the major problem in water is that there is a hardness in the water. If you have seen in the pipeline, we do have a scum or the scaling around the pipeline, so that is something hardness of the water. And so we have two terminology here: the one is alkalinity and another is hardness. So how you will make the difference between these two terminologies? We have four options, and you have to tell me the right difference between alkalinity and hardness. The option are: alkalinity is caused by calcium magnesium salts, while hardness is due to hydroxide and carbonate ions. B option is: alkalinity is a measure of water buffering capacity, while hardness indicate the concentration of calcium and magnesium ions. C option is: alkalinity affect soil absorption, while hardness control the pH of water. And D option is: alkalinity leads to scale formation in pipes, while hardness neutralize acids in water. Okay, so again, I'm having option A and B. So one person, Pradeep, gave me A answer and Venkateshwara gave me B answer. And let me please stick to answer B right now, but I will tell you why. So don't worry about that. Okay, so if I'm talking about the alkalinity, so yes, B is the right answer. So alkalinity is whenever you have uh, hydroxide ion in your water, or you have some kind of chemical that will capture or that will reduce H plus ion, because H plus ion is giving you the acidity in the water. Okay, so the compound or the chemical, either that will reduce H plus ion or that will give you the hydroxide ions in the water, so that will give you the alkalinity. And alkalinity is that will neutralize the acidity of the water. Okay, so if it is reducing or neutralizing the acidity capacity, then it means it is buffering the water. Okay, it is not leading to the rise in the pH, or to decreasing the pH. So for example, if we do have a lot of acid in the water, then alkalinity, some chemicals we will have in the water, that will reduce that acidity. So it means it is acting as the buffering capacity of the water. So that's why alkalinity is the measure of water buffering capacity. It means it is neutralizing the acidity. The thing is very clear. Then if we are coming to the hardness, then hardness is due to the multivalent cations. So we should have cations. It means we should have positive charge on that, and that should be multivalent. For example, calcium 2 plus. So it is multivalent ion, and this is cation, positive. So whenever we will have the multivalent cation in the water, so that will give you the hardness. And if we are talking about the calcium, then this is Ca2 plus, and if it is a magnesium, then Mg2 plus. So these both are the multivalent ions and cations. Along with that, if we do have, let's say, iron, Fe2 plus, this will also give you the hardness. But because in most of the time in water the most prominent mineral is calcium and magnesium, then most of the time what we are saying that the concentration of calcium and magnesium ion will give you the hardness. Okay, so that's why B answer is the right one. Alkalinity is caused by calcium and magnesium salt. Yes, it can be, but if it is let's say if it is the CaCO3, if it is a CaCO3, and if this CaCO3 will dissociate between Ca plus, let's say, CO3 2 minus, then this CO3 2 minus will reduce the concentration of H plus ion. So then you can say, yes, alkalinity may be due to calcium and magnesium, but that calcium or magnesium should be like this: calcium carbonate or magnesium carbonate. And hardness is due to hydroxide. No, this is not due to hydroxide. Hydroxide is OH minus, and as I told you, it should not be minus, it should be positive, means cation, and it should be multivalent. So A is not the right answer. If we are talking about the C, then alkalinity affect soap consumption while hardness control the pH. pH control is the work of the alkalinity because it is reducing the acidity, it is neutralizing the acidity. Then this again is not the right option. Then scale formation in pipe, this is mostly due to hardness, and neutralization of the acid is due to alkalinity, and that's why this is again is not the right answer. So B is the only answer that is right. Okay, so here you can try to understand. Alkalinity is a measure of water ability to resist change in the pH. It means its resistance to become too acidic. And hardness is the measure of the concentration of certain dissolved ion, particular calcium and magnesium in water. And here we do have the example of alkalinity. If we do have bicarbonate, carbonate, hydroxide ions, so these will give you the alkalinity. If you have calcium and magnesium ion, that will give you the hardness. And this is same like as the first point. And just see here, we have bicarbonate and carbonate in the alkalinity because these are neutralizing the H plus ion, so these are neutralizing the acidity. And we have calcium and magnesium in the hardness, so we have divalent salt here. And the mixture of this carbonate and multivalent cation can give you a lot of compound. For example, calcium bicarbonate, calcium carbonate, magnesium bicarbonate, and magnesium carbonate. Okay, so the thing is, just like that, if we are talking about the alkalinity, we are talking about carbonates, bicarbonates, and hydroxides, because these three compounds are mostly used to neutralize the acidity and will help you to neutralize the H plus ion. And if we are talking about the hardness, then this will be the multivalent cations. These cations can be calcium, magnesium, iron, and more than that. Okay, but because uh, calcium and magnesium are prominent in the water, then most of the time we are talking about calcium and magnesium in the hardness. I think this is clear. What's the difference between alkalinity in the water and hardness of the water? Okay, so here I wanted to show you also that if we are talking about the hardness, that can also give you the soap scum, scaling on pipe, and that will leave the stain on plumbing fixture. And total hardness, I already have talked about this, polyvalent or multivalent cations. And we do have two type of hardness. The one is carbonate hardness and another is non-carbonate hardness. And whenever we will sum up, then this will give us the total hardness. Okay, so the next question is based on the difference between carbonate hardness and the non-carbonate hardness in the water. You have to tell me the difference between these two. And the options are carbonate hardness is caused by sulfate and chlorides, while non-carbonate hardness is caused by bicarbonates. Carbonate hardness is also known as permanent hardness, while non-carbonate hardness is temporary. Carbonate hardness can be removed by boiling, while non-carbonate hardness cannot. And the option is non-bicarbonate hardness is due to bicarbonate of calcium and magnesium, while carbonate hardness is due to nitrates. So, what do you think? What should be the answer whenever you are making the difference between carbonate hardness and non-carbonate hardness? You can give me wrong answer, but this is how I will try to give you the right answer in a nicer way. Priscilla gave me answer C with the question mark. Okay, but your question mark should not be question mark because this is the right answer. Okay, so I'm agreeing with Priscilla that C answer is the right one, and I will tell you why. Uh, okay, so we have two type of hardness. One is the carbonate, and another is the uh, bicarbonate. Sorry, non-carbonate. So just see that if we do have the hardness, and I told you hardness is due to multivalent cations. So this can be calcium 2 plus and magnesium 2 plus. Whenever these will react with carbonates, then this will give you the carbonated hardness. Whenever this will react with, let's say, chloride, okay, and more other another anions we have. So if they are reacting with the chloride, let's say, that will give you the non carbonated. Okay, and these are the carbonated hardness. So one is CH and another is NCH. Okay, so from starting we have hardness. Hardness is due to multivalent cations. This can be calcium, this can be magnesium, this can be iron. Okay, these cations can react with carbonate, this can react with let's say chloride. If these are reacting with either carbonate, or it can also react with HCO3, so that will give you the carbonated hydrogen hardness. And if it is reacting, calcium and magnesium is reacting with the chloride, that will give you the non carbonated hardness. This is very temporary. Carbonate hardness is very temporary. Whenever you are boiling, then this will break down, this will precipitate out, and that hardness we can remove. So that's why it is very important for us to boil the water, so that the hardness can be precipitated out and can be at the bottom, and we can remove that. So whenever we are talking about the carbonated hardness, this is very temporary in nature, and this we can remove by boiling. But this is very stubborn, this non carbonated carbonate hardness, this we can't remove by boiling, and this is very difficult for us to remove that kind of hardness. And this is the reason, because we do have hardness in the water. That's why we have to use a large amount of soap to wash our cloth whenever we do have the higher concentration of hardness in the water, and this is very difficult to remove. So that's why C answer is the right one answer. Permanent hardness is due to non carbonated hardness, so this is not the right answer. Non-carbonated hardness is not due to bicarbonate, but it may be due to chloride. Okay, so this is again not the right answer. And carbonate hardness is due to sulfate and chloride. No, we are talking opposite. Carbonated is due to bicarbonate, and non-carbonated is due to sulfate and chloride. So I think the difference is very clear whenever we are talking about hardness, soft hardness or the hard hardness, and you can say temporary hardness or permanent hardness. Is it clear right now? Why we are sticking with C answer but not D, A, or B? Okay, so here you can also see if we have carbonate hardness, then the compound will be calcium carbonate, magnesium bicarbonate, calcium hydroxide, magnesium hydroxide. Okay, and whenever we are talking about non-carbonate, then this will change. This will be sulfate, then chloride. Okay, so I think difference is very clear whenever we are talking about carbonated hardness and non-carbonated hardness. Okay, here, okay, the one thing very important for us to see that if we have calcium and magnesium, this will give you hardness, right? And if it is just associated with bicarbonate or carbonate, if it is not associated with sulfate uh, or chloride, if it is not associated with this, then what we can say is that alkalinity will be equal to hardness. So this carbonated hardness will equal to total hardness, or alkalinity will equal to total hardness, because here just the associated are carbonate but not the sulfate or chloride. Okay, and if we are talking about the non-carbonate, then this calcium or magnesium should be associated either with chloride, nitrate, sulfate. And here how we can calculate, we have total hardness minus carbonated hardness. This is how we will get the non-carbonated hardness. I think this is clear, and based on that we have numerical question, very easy numerical question. I will try to help you to solve that, but before that, this is very important. Just see the units. These units are mg per liter. So how much microgram of that particular chemical we have in per liter of the total water, or ppm as calcium carbonate. I will tell you how we can calculate that, and the important one unit is equivalent per liter and milli equivalent per liter. This is very important for us to know, because based on that only most of the question will be solved. And how we can calculate that, I will show you in the next numerical question. But I think till now it is very clear the difference between alkalinity, the difference between carbonated hardness and non-carbonate hardness. Okay. Okay, very easy question. We in the water sample, we have calcium concentration and we have the magnesium concentration, and you have to tell me what is the total concentration uh, of total hardness in mg per liter as CaCO3. So how we can calculate that? Okay, so very simple. As you know that total hardness is because of multivalent cations, and here the cations are calcium and magnesium. So it means whatever the concentration of calcium and magnesium we will have, if we are doing the summing up of these two concentration, then we will get the total hardness. Okay, because we are not talking here about the anions but cations, and cations here are just calcium and magnesium, right? Okay, the first thing is that. But here the unit, just see here the unit, it is microgram or milligram, sorry, it is milligram per liter as CaCO3. So how we can calculate this? So here we have this concentration. So this concentration is in mg per liter, right? This concentration in mg per liter. And if we want this mg per liter as CaCO3, then what we have to do is, first we have to convert it into milli equivalent per liter. And how we can do this? This will be equal to mg per liter divide by molar mass, and this molar mass will be divided by charge. So for example, if it is the calcium and the value is 40, so this will be 40 divided by a molar mass of this calcium, this is 40.1, and charge. So we know that here we do have 2 plus, then this will be divided by 2. So this is how first we will convert that mg per liter of calcium to uh, milli equivalent per liter. Okay. Then the next thing that we have to do is, because we know that for the calcium the molar mass is 100 and the charge is 2. So this will be 50. So whatever value we will have of milli equivalent per liter, multiply by 50, that will give you mg per liter as CaCO3. Okay, and so we will have the value of calcium in mg per liter at CaCO3, and we will also have the value of magnesium in mg per liter as CaCO3. And whenever we are doing the addition of these two value, this will give you the total hardness. Okay, so the first step will be to convert mg per liter to milli equivalent per liter. Okay, after that we have to multiply it with the 50, because this is associated with the calcium carbonate. And whenever we will multiply this with 50, then we will have the value in mg per liter as CaCO3 for each of the component. Then we will do the addition and we will get the total hardness. Let me show you the answer. This is 141, but I do have solution for this. Let me show you. Okay, so first we are calculating the equivalent weight. So this equivalent weight is molar mass upon charge. Okay, so we calculated equivalent weight of calcium and equivalent weight of the magnesium. Then we have to convert it into milli equivalent per liter. Then what we have to do, this is mg per liter divide by the equivalent weight. This will give you milli equivalent per liter for the calcium, and this is for the magnesium. And then we have to multiply it with the 50. Okay, because this will be as CaCO3, and then we do have the addition of these two. This is how we can calculate the total hardness due to calcium and magnesium. If you have any kind of doubt in any of the step, you can let me know. Any problem with this numerical? Just keep in mind, we will have firstly in mg per liter, then we have to convert it into equivalent milli equivalent per liter. How we can do this? We have to divide this value by equivalent weight, and then we have to multiply this with 50, so that we can have value in mg per liter as CaCO3. if you have any problem, and then we have to do the summation or the sum of these two cations, then we will have the value of hardness. If you have any problem, you can let me know, otherwise we can go on to the next question. Is it clear? Any step that is not clear to you, you can let me know. Should I go further on the next question? Any response from you people? Okay, thank you. Thank you so much for responding. Okay, the next question is the previous question was based on the hardness, right? The next question is based on the alkalinity. And because we know that alkalinity is due to either bicarbonate or carbonate or due to hydroxides. Alkalinity may be due to bicarbonate, carbonate, and hydroxides. And if you know the concentration of these three in the form of mg per liter as CaCO3, and if you are doing the summation, then again you can have the value of alkalinity. Okay, so here what they have given is that a water sample contain 110 mg per liter of bicarbonate. So bicarbonate value is given 110 mg per liter, and molecular weight is also given, so that we can convert that mg per liter into milli equivalent per liter. And it carries a negative charge 1. And what is the alkalinity? So it means we do have alkalinity just because of this one. So these are not required, these two are not required. So just we have to do is, we have value 110 in mg per liter. We have to divide it by the molecular weight, so this is 61, divide by charge, charge is 1. So this is how we will get milli equivalent per liter, right? And whenever we will multiply it with the 100, sorry 50, then whatever the concentration we will get, this will be in mg per liter as CaCO3, and this will give you the alkalinity. So we just need the concentration of bicarbonate in the form of mg per liter as CaCO3. So just this is we need to do, right? And based on that we will get the answer. And let me show you how we can do this. Equivalent weight, so this will be molar mass by charge, so this will be your equivalent weight. And if we want to convert milligram per liter into milli equivalent per liter, then 1110, this is the mg per liter, divide by the equivalent weight, and this we calculated by molecular weight multiply divide by charge, and this will be 1.80. We have to multiply this with 50 because we are calculating it in the form of calcium carbonate, and this is how we will get the 90.1 mg per liter as CaCO3. This is how we can calculate the these are very simple numerical question. If you have any problem, you can let me know, because the concept is very clear. You will have the value in mg per liter. First you have to convert that into milli equivalent per liter, then you have to multiply it with 50, so that you can have value in mg per liter at CaCO3, and this is how the question will be solved. Okay, coming to the next question, and it is, if the total hardness is 141 mg per liter and alkalinity is 90 mg per liter, and both are as CaCO3, can you calculate the carbonate hardness? Very simple, based on just one concept, not any calculation, nothing like that. So we talked about that if we have the hardness, total hardness, this total hard, I got a, okay, it is the calcium carbonate. I asked about the calcium, sorry, carbonate hardness, but not about the non carbonate hardness. You are going reverse to that. Yes, so we have total hardness, and the this will be carbonated hardness plus non carbonated hardness, and this carbonated hardness may be equal to alkalinity, right? And if we have just carbonated hardness, and if we do not have carbonated hardness, then alkalinity will equal to hardness, total hardness, if this is zero, right? If it is zero, then total hardness will be equal to alkalinity only. And here it is given, total hardness is 141 and alkalinity is 90.1. Then the question asked is the carbonate hardness, because here we do not have non carbonated hardness, right? So how we will calculate this, let me show you. So this will be 90, just see here. If we are calculating the carbonate hardness, this will be the minimum value of total hardness or alkalinity. So this will give you 90.1 only. I think I gave you wrong, I think here, but just thing is that we have here 90, and this alkalinity is giving you the carbonated hardness. It means we also have non carbonated hardness, and this non carbonated hardness will be 141 minus 90.1, right? Okay, we are going to the next question. Okay, this question is, as I already have discussed with you, total hardness is 141, carbonated hardness is 90.1, then what will be the non carbonate hardness? Venkateshwara gave me answer of this question in the previous question, I think. Anjali gave me a answer, that is 50.9. Then obviously this will be the answer, because total hardness is due to carbonated and a non-carbonate, and if we are subtracting this 90.1 from 141, then we will get a option, right? Then yes, a is the right one. Okay, the next is, we have carbonate, bicarbonate, and bicarbonate is in the form of mg per liter. Molecular weight is also given, charge is also given. Then can you calculate this is in mg per liter as CaCO3? So that will give you the right answer. So this is mg per liter as CaCO3, and this is your carbonate. Can you match the right? So this will be what? We have mg per liter. So mg per liter divide by molecular weight, divide by charge, multiply by 50 will be equal to mg per liter as CaCO3. So now can you give me the value of uh, bicarbonate in the form of mg per liter as CaCO3? 110 divide by 61 divided by 1 multiply by 50. Can you tell me now the answer? So this will be 90.1. Just see here. 1110 divided by 61 divided by 1. This will give you 1.80 multiply by 50. This will give you 90.1 mg per liter as CaCO3. Okay. I'm having more question on hardness because these are the most frequent question asked in any of the book that is related to the air pollution. So that's why I'm trying to make you very excellent in this topic, maybe. Okay. Anyway, so if we have water sample, okay, in water we have calcium concentration and we also have magnesium concentration, and you want to calculate the total hardness, then can you calculate? Again, very simple. You will calculate is in the form of mg per liter as CaCO3, this one, and then this will be summation, and this is how you will get the total hardness, right? So can you tell me the molecular mass of calcium and molecular mass of magnesium, because we have to convert it into mg per liter CaCO3. Molar mass of calcium, this is just mostly the double of your atomic number. Atomic number of calcium is what? Is it 20 or what? 18? Anyway, so let me show you. Okay. So this is the formula that we know. If we want to, Venkateshwara gave me 20, yes, this 20 is the right. So if we want to convert mg per liter into milli equivalent per liter, then we have to divide it by molar mass divided by charge. So if we are talking about the calcium, and this is known as the equivalent weight. This is known as the equivalent weight. So first we are calculating the equivalent weight. So this will be 40 by 2, 20, approximately 20. For the mg magnesium, this is 24 by 2, this is near to 12. So these are the equivalent weight. Then we want to convert it into milli equivalent per liter. Then whatever value we had in mg per liter divide by this equivalent weight. So this is how we have converted into milli equivalent per liter. Then we have to multiply it with 50, because we need to convert it into mg per liter as CaCO3. Whenever we will multiply it with 50, we will have some value. Then we will do the summation. And this is how we will get near to 166 mg per liter as CaCO3. So very simple. You have concentration in mg per liter. You have to convert it into milli equivalent per liter. And how you can do, this is the formula how you can do this. Then you have to multiply it with 50 so that you can have value in mg per liter as CaCO3. Then you will do the summation. This is how you will calculate the total hardness. So if you have any value of calcium, magnesium in mg per liter, you can calculate hardness, total hardness very easily. There should not be any doubt with this, right? Anyway, this is okay. So if you know, like if we have calcium carbonate, right? Or if we have, let's say, calcium chloride. So, and if we are breaking it down, so this will be Ca2 plus, and this will be CO3 2 minus, and this will be Ca2 plus, and because here we do have two chloride, right? So this will be 2 chloride, and chloride have the minus 1. But if you will see calcium, calcium, so we have 4 cation charge, plus 2 plus 2. Okay, and so these are the cations. And if we are talking about the anions, so this will be 2 minus, so minus 2. And here we do have two molecules, and but one charge, so this will be again -2, so this will be -4. So if we are doing the summation of cations and anions, that should be is equal to 0. Okay, so whenever in the water we have cations and if we have anions, and if we are summing up, that will give you 0 value. And just keep in mind that value 4 or -2, that should be in milli equivalent per liter. Okay, that should be equal in milli equivalent per liter. And if it is a 0, then it means whatever test we are undergoing, that test is true. But if these are not equal, cations is not equal to anion, that means we do not have charge balance and we do have some error. It means we are doing the analysis that is wrong. Okay, so here we have a lot of anions and cations. We have sodium, we have potassium, calcium, magnesium. So these are the cations. We have anions, that is carbonate, bicarbonate, sulfate, calcium, and nitrate. Okay, then the thing is, uh, first we have to convert these ions into mg equivalent per liter. You know that how we can convert that. And then we are summing. Okay, and for example, if we have 4 milli equivalent per liter of the cations and 2 milli equivalent per liter anion, that means we will have the error of 2. Okay, that means we will have the error of 2. So likewise, based on these values that is already given, can you calculate the error, and that error is acceptable for us or not? So let me show you how we can calculate this. If you have any problem, if I'm like going very fast, you can let me know. But okay, just see here. What we need to do is we need to calculate that into milli equivalent per liter. Okay, and how we can do this? As I told you, this is the mg per liter, divide by molar mass upon charge. So this is how we calculated milli equivalent per liter of calcium, magnesium, sodium, potassium. So these are the cations, and we will do the sum. So these much milli equivalent per liter cation we have. Okay, this is how we also calculate the anion concentration. So for carbonate, for sulfate, for calcium, sorry, for chloride, for nitrate. So this is how we will have the sum of the anions. Okay, then what we will do, we are calculating the difference between cations and anions. So this will be this much. And if we are calculating the percentage error, then this will be difference divided by sum of cation multiplied by 100. So the difference is near to 3.90. And if this percentage error is less than 5, then this means our chemical analysis is acceptable. But if it is more than 5%, it means our chemical analysis, we are doing something wrong in our chemical analysis, that our cation and anion are not equal and the error is more than 5%. Just you need to do is you just need to calculate this into mg, from mg per liter to milli equivalent per liter. You have to do the summation of cations, you have to do the summation of anion, you need to subtract it, calculate the percentage error, and this is how you can tell whether your analysis is correct or not, because anion and cation should be equal. Okay, yeah, I think this is clear. So whatever, so these are the concentration in mg per liter, these are again the these are the cations, these are the anions. We need to convert that into mg per liter, and we have to separately, we'll do the summation of cations and anions. We will have the difference, then we will calculate the percentage error. what percentage error we have, because hypothetically and in the real world cation should be equal to anion as per the equations of the chemical equation we should have, right? I don't think that this is like much more chemistry. I think this is just a little concept of chemistry. Okay, so we have calcium and we have magnesium, and this is giving us the hardness. But can you tell which ion is giving you the more hardness? Either it is calcium or magnesium. If we want to calculate like which one is contributing more, then again we have to convert it into mg per liter CaCO3. Which one have the more value in this form, that will give you the more contribution. No, this will be calcium only. Let me show you. Uh, okay, so just see here. If we are converting into if we are converting into mg per liter as CaCO3, then for the calcium this is 87, for the magnesium it is 78. So calcium is contributing more to the hardness. Okay, no doubt initially the values were like very initially the value were 31, 35 and 19, but if we are calculating it in mg per liter CaCO3, then this will be 87 and 78, and 87 is more than 78. It means calcium is giving you more hardness. Okay, based on the concentration of calcium magnesium that we have in the sample in mg per liter initially, and then we are converting that. A little boring, but you have to digest these all concept. Okay, the next question is total dissolved solids, TDS. If you have heard, like whenever some RO person come to your home, and that the first step is that person will calculate the TDS in your water, and that person will tell you, okay, TDS is very high, I think you should have RO in your kitchen. Okay, so but how we can calculate that TDS? And so the formula of TDS is in mg per liter, and this we can calculate by the one formula, that is A multiplied by EC, and this EC is what? Which conductivity? Electrical conductivity, right? So this is electrical conductivity, and you have to tell me the this value. Most of the time this is the constant, and we have to take the some constant value for this. And this electrical conductivity is just we can calculate using one electrical conductivity meter we have. If we are putting that meter into water, that will give you the electric conductivity. We are multiplying this with the A, that will give you the total dissolved solid. Let me see who gave me the answer. uh, Samir gave me C answer, and Archit also gave me C answer. Yes, I agree with the C, that the A value, this constant value, is mostly zero point 0.5. Zero point 0.5 multiplied by EC, that will give you the total dissolved solid in water. And can you tell me, like for the drinking water, what should be the value? Like above that, we should not have the value of TDS. That will give you different taste, or like, so this is the physical parameter of the water. Anyway, so I think next question will be based on this only. If we have TDS, Samir gave me 500 mg per liter. Yes, actually it is 500. So for drinking water, if your TDS is less than 500 mg per liter, then we can take that water to drink. Otherwise, we should have something that can remove that TDS. Anyway, so based on TDS, we have different water type, and you have to tell me which water have what kind of TDS range. So we have fresh water, brackish water, saline water, and seawater. And based on that, you have four options. So can you tell me why and what? Venkateshwara 200. This is 500 mg per liter. Samir gave me D answer. Archit also gave me D answer. What about A answer? Just see. Whenever it is less than 1500, then this is the fresh water. After fresh water, there will be the brackish water. This will be 1500 to 5000. More than 5000 will give you saline water. And for the sea water, TDS is very high. So Pradeep gave me A answer. So Archit and Samir, is it okay that I'm giving you A answer, not giving you D answer? First, we will have the saline, sorry, fresh water. Fresh water will have the minimum value of TDS. Then brackish water will have little more TDS. Saline water will have more, and seawater will have um, like the largest TDS value. Okay, thank you so much. So that's how A answer will be the right one. Okay, so we talked about alkalinity, right? We talked about hardness. We talked about TDS. The next is, and we are talking about pollutant concentration in water, right? The one parameter by which we can see how much our water is contaminated or having different unrequired pollutant or contaminant, it is sodium adsorption ratio, and this is used to evaluate the suitability of water for irrigation. And you have to tell me the correct formula to calculate sodium adsorption ratio. Venkateshwara Pradeep gave me A answer. Okay, yes. Mm, okay, Samir gave me C, but no, I agree with A answer. So this is this is the formula that we have to cramp. So don't worry if you are giving me the wrong answer, because we do not know the formula most of the time. So this is the formula. If we have sodium and divide by the root of calcium plus magnesium divide by 2, so this is how we can calculate the sodium adsorption ratio. And based on that, we will decide whether our soil is or whether our, so not soil, but our water is useful for the irrigation or not. Okay, and this is related to the clay. So we have the clay, right? And if we do have higher amount of sodium absorption ratio, or if we have higher value of sodium absorption ratio in the water and then in the soil, then what will happen? The soil will be degraded. Okay, because we have higher SCR. Less than, someone told me, SCR less than 25. Okay, the next question is on that only. So I also have the explanation. So just wait a little. My light went down. Anyway, so the next question is, according to SAR value, which of the following statement is correct? And these are SAR less than 3 indicate that water is unsuitable for irrigation. 3 to 5 indicate safe water with no restriction. More than 9 means water is not suitable for irrigation unless in India, where SAR is less than or equal to 26 may still be allowed, and SAR equal to 15 is universally acceptable for irrigation purpose. So the answer is Pradeep gave me C answer, and that is right. So more than 9, this is not suitable, and in India, but we can have value whenever it is less than 26 or equal to 26, that may still be allowed. Let me show you the concept. Okay, so if it is less than 3, then water is suitable for irrigation purpose. If it is between 3 to 9, then we may have some restriction, but still we can use this. If it is more than 9, then it means water is not useful for the irrigation. But in India, we have set this value to 26 because sodium does not build up in soil and cause damage, because every monsoon season the soil is thoroughly flushed and renewed. So that's why we are not taking the value 9, but we are taking the value 26, because every monsoon this sodium will be flushed out. Okay, so that's how that C answer was the right one. Okay, what is the main reason why excessive sodium in irrigation water leads to poor soil health? And we have four options. Sodium causes clay particle to dissolve and enrich the soil with nutrient. Sodium ions strengthen the bond between clay particle, improve soil structure. Sodium replaces calcium magnesium on clay particle, causing clay dispersion and pore plugging. And sodium increases the microbial activity that hardens the soil. So why it is said that whenever we have higher value of sodium in the water, irrigation water, that will give you the poor soil health. Why this is happening? Pradeep gave me A, that sodium cause clay particle to dissolve and enrich the soil with nutrient. The first part was right. This part was right, but this is not right. So that's how A is not among the right answer. C is the right answer. So what is happening is that we have calcium and magnesium. So calcium and magnesium, and these are the cations, right? These are the cations that we have. Okay, and among that, we in the clay particle we also have anions that are the negatively charged. So we have the anions that are negatively charged. So what will happen? That positive charge will make some bond with that negative charge of the clay particle, and this is how that will form the pores, that will form the comb like structure. And so this is how the in actual the clay soil is. But what will happen if this will be replaced, calcium and magnesium will replaced by the sodium, then what will happen? This will break down this porous structure, and this porous structure will be dissolved. And because there will not be any reaction, so we will have the grain of the clay particle that will go inside the pores, and that will plug that also. So you can read more about this, but C answer is the right one. Okay, if you want to calculate the sodium percentage in the irrigation water, then what is the formula? How we can calculate that? And keep in mind that this is in mg milliequivalent per liter. So if you want to calculate the sodium percentage, then how we can calculate? This is very simple. If you want to calculate the sodium percentage, very basic, like from the maths only. Pradeep gave me B. Yes. So this is something percentage of sodium and then all the cations that we have, and this is divided by all the cations. So this is how B answer will be the right one. Okay, so we were talking about RSC. So what is this RSC? Can anybody tell me the full form of this RSC?
Residual sodium carbonate.
Yes. So this is residual sodium. And what is C? Residual sodium.
Carbon.
Okay, so this is carbonate, right? carbonated. So how we can do this? So whenever will have the um, carbonated anions minus, we have the cations. So whenever we are subtracting this, then we are having the formula of RSC. Then you have to tell me the standard by which we can tell whether water is suitable for us for the irrigation or not. So this is 2.5, 1.5, and 2.5 more than or less than 1.25 or more than 2.5. So can you tell me which one is the correct for the water suitability based on the RSC value? Pradeep gave me D answer. Okay. So D answer is the right. Whenever we will have the water that have the RSC value more than 2.5 milli equivalent per liter, then we will can tell that water is not suitable for irrigation, right? Okay, so coming to the, okay, so because one of the lecture 12th lecture that sir has delivered to you is based on the quality standard only, and in air pollution also we talked about the criteria pollutant and what value we should have. Above that value, the value should not be exceeded, right? Likewise, we also have some standard in the drinking water quality. And for example, if it is a color should be colorless, odor should not be objectionable, then turbidity should not be more than 5 NTU. And if we are talking about the dissolved solid, this should not be more than 500. pH should be between 6.5 to 8.5. If we are talking about the total alkalinity, we understood how we can calculate that this should not be more than 200 mg per liter. If we are talking about the total hardness, just see the unit, this is in mg per liter, and total hardness is in the form of mg per liter as CaCO3. This should not be more than 300. So I just wanted to show you that we have standard not just for the drinking water, we have standard for the irrigation water, we have standard for the emission industries is releasing some water in the river. So before releasing that water into the river, what should be the concentration? So for that also we do have some standard. So likewise we do have many standard based on that, so that our water that we have in the form of river, in the form of groundwater, in our kitchen should have very like not objectionable value or threshold objectionable concentration of particular pollutant, right? Okay, so likewise, we should have the value of chloride, fluoride, sulfate, nitrate that is given in the drinking water. Anyway, again, I have one question on bicarbonate concentration, but I think I should skip this because we already have calculated a lot of alkalinity and hardness based numericals, right? So right now I'm skipping this. Okay, you can calculate this one. If we have the calcium and sodium and we do not have potassium, then can you calculate the percentage sodium? So the percentage sodium will be 2 upon 3 plus 2, right? Or if we are calculating, so this will be in milli equivalent per liter. But if we want to calculate into the form of mg per liter as CaCO3, then this will be changed because we have to change that value. But anyway, so let me show you. Yes, C answer is the right one. So this will be 2 divided by 3 plus 2, and this is how this will be 40%. And this value is below the irrigation limit, that is 60%, so water can be safe for the irrigation. Okay, so can you calculate here the RSC value and can you classify whether our water is useful for the irrigation or not, will come under safe threshold or marginal threshold or unsuitable threshold. So what was that residual sodium carbonate value? So this one, why calcium carbonate is taken as the equivalent benchmark for the standard, because most of the time in any of the water we do have the concentration of calcium carbonate. So the prominent amount is in the form of calcium carbonate. So whenever we are talking about like any of the alkalinity or hardness, we are first converting into calcium carbonate because this is major constituent in the water. Anyway, so first we have to so this was nothing but carbonate anion minus, so these were the carbonate anion minus cations. So this is carbonate anions and these were the cations. So this will give you the value of rsc. So can you calculate this? So this will be 0 and let me show you how. So this was the formula. We have carbonates and these are the anions because we have the negative charge, minus we have the cations. And we didn't have this carbonate, we had the bicarbonate 3, and this value we already have given, and this is how we will have the 0 milliequivalent per liter. And because this is less than 1.25, it means it is safe for the irrigation. Okay, coming to the next. Okay, so till now we solved some question on water pollution and we learned about the criteria pollutant, primary and secondary pollutant in the air pollution. Now we are moving to some instruments by which using that we can analyze. So for example, if we are talking about the concentration of sodium we have in the water, then we have some instrument by which we can measure directly. So and we should know the principle of that instrument or the techniques. So the one of the technique is chromatography. Okay, and you have to tell me the principle of chromatography. And here we have four options: separation based on solubility in water only, separation based on difference in partition between stationary and mobile phase, separation based on melting point differences, separation by evaporation under heat. So everyone is giving me the right answer, that is B. So the separation is due to because we have two phases, stationary and mobile phase, and based on that we can separate some organic compound or we will talk about the compound, what kind of compound we can measure using the chromatography. Okay, so B is the right one answer, but let me show you the principle of firstly the gas chromatography. So what will happen, we have some gas, that gas is the carrier, so this will be your mobile phase. Okay, so this will be your mobile phase. Then you will have some sample. Okay, then you will inject that sample in the form of gas. Okay, if we are injecting that sample into one column, okay, and we are giving gas to that column also. Okay, so what will happen, and in that column, just see that column, that column have tube and packing and also have some silica. So silica means, or it may have liquid phase also. uh, so silica means it is your stationary phase. So here your mobile phase is gas and your stationary phase is silica. So what will happen if we are injecting any gas into that column? So what will happen? That gas will flow in that column using that carrier gas. Okay, but what will happen? That sample may get absorbed into that stationary phase also. So some of the compound or some of the atom or molecule will be absorbed, and then some of the molecule will not have that tendency to attach to that column or the to the silica. So what will happen, some of the compound, let's say I'm just taking one random example. So for example, in the sample we have calcium, we have nitrogen, and we have phosphorus. Let's say the tendency of calcium or the carbon is less to attach to the silica. Then what will happen, this will go out firstly in the detector. Okay, so this will give you, so if we are talking about this is time, right? This is time and this is the concentration. So if the tendency of calcium to be attached to the silica is lesser, then it will take very less time to make the peak. So let's say this is the peak of calcium, carbon. Then let's say nitrogen is taking nitrogen is attaching to that silica, then the time will be longer and that will make again one peak. And let's say this is for the nitrogen. So based on whether it is getting adsorbed or absorbed by the gas or by the stationary phase or by the mobile phase, the peak will be different at the different time. So based on that, using computer or data analysis, we can tell which one. So if the peak is, let's say, at 20 second, or let's say this is the peak at 5 second, so based on time, based on the peak, we can identify which kind of compound or which kind of atom molecule we may have in the sample. Okay, so this is the one technique, that is the gas chromatography, by which we can identify in the sample. So let's say it is a water, and in the water we may have calcium, we may have magnesium, we may have nitrogen. So if we want to see the presence of these kind of chemicals in the water, then we may do gas chromatography, because the characteristic of each of these compound to be attached to the stationary or to the mobile phase will be different, and based on this separation we can identify uh, which chemical we have in the, let's say, any sample. So this is the principle. I think this is clear. Okay, this is again I wanted to show. So this is the column, right? Column has the stationary phase because this is the silica. At mobile phase we have the gas, so this is the carrier gas. So just see here, we will have a lot of atoms into that sample. So some atom will be attached, some atom will attach, so the time will be very different to create the peaks. Okay, no doubt every atom will go out because we are having the flowing mobile phase, so every atom will go out, but the thing is the peak will be different at a different time. So based on that peak we can analyze which chemical it may be. Okay. Okay. In gas chromatography, the mobile phase is typically what? A high boiling liquid, a low boiling solvent mixture, inert gas such as helium, and polar stationary phase. Pradeep is very fast. Venkateshwara also. So both gave me answer C, and I'm also agree with answer C. That is helium. Priscilla also gave me C. So if we are talking about the gas chromatography, means the mobile phase will be gas, and this gas will be inert. So one of the inert gas is the helium. So helium is the mobile phase that we are choosing in gas chromatography. Which of the following is not an advantage of gas chromatography? We have four options: high separation efficiency, ability to separate volatile compounds, low sample consumption, effective for non volatile and thermal unstable compounds. Priscilla gave me D answer. Okay, first C and then D. Okay, Venkateshwara also gave me D. Yes, I'm also agree with the D answer that uh, we have some advantages of gas chromatography, but along with that we also have some disadvantages. And one of the disadvantages is that whenever we are talking about the thermally unstable compound or non-volatile compound, then this can't be measured using this such kind of technique. So these are not the advantages, but these are the disadvantage of gas chromatography. So let me show you the advantages and disadvantage. So if we are talking about the advantage, then high separation efficiency. It can separate or it can have more than 200 chromatographic peaks in 2 hours. So just see that how good separation efficiency it has. Then even we do have small sample and so even if we have small sample size or sample concentration, uh, then only we also have utilize this. So small sample consumption and high detection efficiency. So 1 ml of gas sample is enough for gas chromatography. If we have liquid sample, then zero point 0.1 microliter is enough for us. And if we do have solid sample, then few mg of solid sample is enough for the detection. Then gas chromatography also have good selectivity, and then wide range of application it has, because it can be used to analyze gas and volatile organic substance. Okay. And under some certain condition, it can also used to analyze high boiling point substance and the solid sample also. And if we are talking about the disadvantages, then it can be only used to analyze the volatile substance. Okay. And the one of the major problem is that the leakage. So there may be leakage because the mobile phase is gas. So this is the another problem. One problem is that this activity is for more polar analytes only. And you can read here, we also have some disadvantage related to the gas chromatography. And here we can't so we can use it whenever we have high volatility volatility compound. We If we do have thermal stable compound and low molecular weight compound, that compound we can measure. But the compound that we cannot analyze is that the compound that do not vaporize or that are highly reactive or chemically unstable. So these are very difficult to analyze. So these are some disadvantage and advantage of gas chromatography. Okay, because we have some peaks, right? So it means to detect that peak we need some detectors, right? We need some detector. So which detector is most suitable for detecting impurities at ppm levels? Which detector is mostly used whenever we do have like let's say water, and in that water we have some impurities, and to detect that impurity even at ppm level, so which detector is most suitable for us? Priscilla gave me answer B, that is fid. Yes, I also agree with this. So we have a lot of type of detector, and the one is flame ionization detector, that is suitable whenever we need to detect the impurity even at the ppm level. So B answer is the right one. Okay, the thing is we had some disadvantage of gas chromatography, right? So to remove that disadvantage, we moved to HPLC. Can you tell me the full form of HPLC? High performance liquid chromatography. Okay, so we are having the chromatography where mobile phase is not gas but it is liquid. Okay, mobile phase is liquid, and we do have high performance. So high performance means we are giving pressure to the mobile phase. Okay, so we have some pressure motor, so we are giving the pressure to the mobile phase that it has to move. Okay, so this is how this is giving you the high performance liquid chromatography, removing the disadvantage of gas chromatography. And in which so you have to tell me whenever the stationary phase, you have to tell me the stationary phase in the reverse phase chromatography. It means in HPLC we also have different type of chromatography, and one type of chromatography is reverse phase chromatography, and you have to tell me in that what will be the liquid stationary phase. Priscilla gave me B answer, that is non-polar C18 material. Yes, you are right. So if the HPLC is reverse phase chromatography, the stationary phase will be non-polar C18 material. And let me show you. So this is HPLC. Here you have pump. Okay, and that, and you have a column, and that and you have the some solvent, so that's how the mobile phase is liquid, and then we will detect. So this is the principle of HPLC. And we do have different phases in HPLC, if it is a normal phase, reverse phase, ion exchange, or size exclusion. So we were talking about the reverse phase. So in that reverse phase, the column packing is non-polar. Means stationary phase will be non-polar, and mobile phase will be water or a miscible solvent, for example methanol, and this we can use to identify the sample that are polar, non-polar, or ionizable samples that we have, right? So we have different phases we can select or we can put based on what kind of compound we have, what kind of sample we have. Okay, so different phases we can have. In the HPLC, we have one terminology. The one terminology is retention time. So this can be defined as what? The time between injection and baseline return, time between injection and peak apex, time between injection and sample loading, time between mobile phase start and stationary phase contact. So the answer will be B. So this is the time. Yes, Priscilla gave me right answer. So this is the B. That is the time between injection and when we will have that peak. So just you can see here in the figure, we have TR at above at the top. We have TR, and this is nothing but when we have injected the sample and whenever we will have peak. So what time it took to create that peak. So this will be the retention time. Okay, so one of the chromatography is size exclusion chromatography, and you have to tell me what happened in that. So, smaller molecule elute first, larger molecule elute first, molecules elute in random order, polar molecule elute first. What do you think? What happened in size exclusion chromatography? Pradeep gave me B answer. I also agree with this one. So just see here again the same slide, but see the last mm, last point, size exclusion. So molecule diffuse into pores of a porous medium and are separated according to their relative size to the pore size. Larger molecule elute first and smaller molecules elute later. So based on that, the answer will be that one only. Okay, now we are going to the spectrometry. So the thing was that uh, we were just identifying which that chemical we may have, right? So based on that peak we could have identified, okay, it can be calcium, it can be magnesium, or it can be chloride. But what if we want to know the concentration of that particular chemical in the sample? Then to know the concentration we need spectrometry. Okay, so spectrometry means we are taking the help of radiation and the reaction property of that interaction of radiation with the sample, and based on that we can tell the concentration of that particular chemical in the sample. Okay, so one of the spectrometry is UVVIS, ultraviolet and visible radiation. Then you have to tell me, there is a one law that giving us the relation between absorbance, concentration and path length. Okay, and someone already have given me the answer. Venkateshwara gave me B. Priscilla also gave me B answer. Okay, so yes, this is the Beer-Lambert law, which relate the absorbance, concentration, and path length. Let me show you how. So, for example, this is our sample, and sample may have some color, right? And if we do have some rays that are incident to our sample, then what would happen? Some light will be absorbed and some light will be transmitted. Okay, and that absorbance will be directly proportional to the concentration. Okay, so A will be proportional to C. How much concentration that we have in that sample, based on that, there will be more absorbance, more concentration, more absorbance. And this law will come under Beer Lambert law. And because we also have path length, so the size of the cuvette, this will be L. And then we have one formula, that is the A is equal to epsilon CL. So epsilon is molar absorptivity, so this is the constant value. C is the molar concentration and L is the optical path length. So based on that formula we can uh, calculate the molar concentration of that particular compound, if we do not, if we know the absorbance, right? And this is the principle of spectroscopy. We will have some light source, and then we will select some wavelength of which light we just need. So if we need the ultraviolet and visible spectroscopy, then the wavelength that will define the ultraviolet and the visible, so means 200 nanometer to uh, 600 nanometer, we will select that range of the light only. Then we will give that light to the sample, and then whatever absorbance we will have, whatever transmission we will have of the light, that will be detected by the detector, and that can give you the concentration based on this spectroscopy. So based on the radiation you can have the value of the concentration. So this is the principle. I think you can read this later, but just one line I'm reading. Spectroscopy is the study of the property of matter through its interaction with various type of radiation. Okay, and for example, if we are taking ultraviolet radiation or visible, then this will be UVVIS spectrometry, right? Okay. Which material is preferred for UV-VIS cuvette to avoid uh, absorption in UV region? So glass, plastic, quartz, and steel. Priscilla Venkateshwara gave me C answer, that is quartz. Yes, so we are using material quartz for cuvette formation. So such kind of cuvette, you must have seen the spectro photometry in your labs. So we do have a little cuvette, a size of that, and that cuvette is made up of quartz, and this these are very expensive. If you will break it down, then you have to give the fine to your institute. So the thing is, they are made up of quartz so that they avoid the absorption in the UV region, right? So that's why it is made up of the quartz. Okay, so the thing is that whenever we are having some light coming and incident on your sample, then what will happen? That sample will be excited. Okay, and electron will be released, and then that will give you some light and then intensity. Based on that intensity, you can have again have some concentration measurement. So in UV-VIS spectroscopy, pi-pi transition occur in compound that contain what? So I got Venkateshwar and Priscilla gave me B answer. Yes. So if we do have electrons, pi electron, so that pi electrons can give you the pi-pi transition. So that's how B answer is the right one. The next is the UV region corresponding to which wavelength range? You must know the wavelength range for that particular region. Do you know the electromagnetic radiation spectrum? If you know that, based on that, you can select. Okay, Venkateshwara gave me A answer. Yes, I also agree with this. If you have range from 200 to 400 nanometer, that will come under ultraviolet. 400 to 700, that will come under visible. More than that, that will come under infrared, right? So A is the right answer. Okay, the another type of spectroscopy is FTIR. You can tell me the full form of this. No doubt I will tell you. But in that, we also have one interferometer, and that split light into two beams. And you have to tell me using what. So we have four options: prism, diffraction grating, beam splitter, and quartz lens. And I got answer C from Priscilla. Yes, I also agree. So C is the right answer. Let me show you this one. So in the last question, we were talking about UV-VIS spectrometry, right? But in spite of taking ultraviolet radiation, we can also use infrared source. Infrared source, and if we do have infrared source, then that will be FTIR. So that would be different type of spectroscopy or metry where we are using infrared radiation in place of ultraviolet or visible light range, right? And in that we have beam splitter that will split, and that will give you one particular range of wavelength to the sample. Okay, so this is the beam splitter. Can you tell me what kind of advantage we have of FTIR? So this is the one type of spectrometry and over dispersive instruments. Because I have less time, then yes. So we do not need any calibration required, so that there is an advantage of FTIR. In UV-VIS spectrometry, we are using lamp that have hydrogen and deuterium. But why? Why we are using that particular lamp, hydrogen deuterium lamps for the light source? Because if it is the ultraviolet visible spectrometry, then that will cover whole ultraviolet region. So that's why we are using the lamp that have hydrogen deuterium. Yes, C is the right answer. This is just for the explanation that we need some source that can give us the light, and then we will select some wavelength out of that, which is not a disadvantage of UV-VIS spectroscopy. And this is it can analyze gas and solid directly. So this is not a disadvantage. Okay, uh, now we have something like this. One question is on air pollution. So for example, we have ocean, right? Or you can say the river, and we have in the atmosphere we have oxygen. Okay, so how much oxygen will be absorbed by that ocean or the river? This we can calculate using one very simple formula, and this is based on that. Also, we have one question. So, if you want to calculate the dissolved oxygen in the water in the treatment plant, and kh, so this is one constant is given, so this is the Henry constant, and the value for a Henry constant is also given, and the molar mass, one molarity of oxygen is also given, 32 gram per liter. So can you tell me how much of the oxygen will be dissolved in the river, or let's say ocean, or any aerated water? So this we can calculate using Henry's law. So Henry law is, in the atmosphere we have the oxygen, we have carbon dioxide. So what pressure, what partial pressure it is giving to that river or to the ocean, this will be the proportional to how much solubility of that gas we will have in the ocean. Okay, so it means the partial pressure of oxygen will be proportional to the solubility of that oxygen into ocean. Okay, and whenever we are equating this, then we will have the Henry constant. So based on that, what we just need to do is, we have very simple formula. This formula is concentration of oxygen will be equal to Henry constant multiplied by partial pressure of oxygen, and we know that in atmosphere we have 21 percentage of oxygen, so the partial pressure will be 0.21 atmosphere. Okay, and if we are multiplying this partial pressure with the Henry constant, then we will have how much concentration we will have of oxygen into ocean water. So this is how we can calculate. I think these questions are not much important. Okay, this one may be the last question that I should explain to you. So, if we do have concentration of thorium in sand, then how much thorium is present in 100 kg of sand? So, they have given some concentration in the sand. Then, if we are increasing that mass of the sand, then how much concentration we will have? This is literally based on your density, volume and mass. So and you know that density is equal to mass by volume. So this is something like this: if you have 100 kg sand, then 100 kg you will calculate the volume based on your density, and then if you want to calculate the amount of thorium, then what you will do, you will multiply your volume to 0.40. So this is how you can calculate, and these are the question related to molarity, molality. I don't think that I need right now to solve such kind of question, because these are ninth or 11th standard question, and I think I will share that PPT to you, and based on that you can solve these questions, right? So I think these are like 5 6 question, numerical question only I had, but right now I should stop because this is again the dinner time. And thank you so much. If you have any query or suggestion, you can let me know. Otherwise, you can go and you can have your dinner. And I ask for suggestion. If you have any suggestion, how should I teach? How should I like make you very comfortable? So you can tell me. And whenever you have any problem, you can write in the chat box, or you can write me in the email. I will try to give you answer on time. And again, next week we will meet from 7 to 9 p.m. only. So thank you so much.